Hey everyone, welcome back to the Topos Institute Colloquium. Today we're very happy to have Christoph Benzmüller talking about many logics, one methodology on the virtues of logic key in computational metaphysics and ontology. So please, Christoph, whenever you're ready.
Yeah, thank you very much for the invitation and the honor to speak here in the Topos Institute colloquium. You mentioned the title. This talk will have two parts. The one where I talk about this methodology, which I call logic key. It's about logical pluralism, and I will show you what I mean by that and how we apply it will be then shown in the second part, where I will have a demonstration of that methodology in philosophy, in what I call computational metaphysics. This latter part in particular is then joint work, and I'm very happy to have him here with Dana Scott. So we just published on that together last year, and I'm reporting parts of the experiments we conducted and reported in that joint work. Yeah, so this presentation is in a kind of adaptive. In the second part, I have lots of material prepared in this demo part, but I can be adaptive there and leave out certain parts. We probably anyway can't go through all of that. And that means I'm also happy to take questions now during the presentations. I just have to cut out then eventually a bit more on this demonstration part. So don't be shy, and if you have questions, just interrupt me. Let's start. I want to start with some introductory remarks, actually, that I have, namely, well, yeah. And this is on logical and mathematical monism, or if you want to be a bit more provocative, even imperialism. And by that, I actually mean a situation where folks shows just some particular logical foundations, for example, for pragmatic reasons or whatever reasons, don't question them really ever again, and then commit to them a priori in developments of mathematical content, for example, mathematical libraries that we build up with proof-assistant technology, for example. So what I mean by that is commitments like this here. There exists self-identical X, so there exist objects a priori, our types that we assume are non-empty. That is a typical assumption that classical logic makes. And there are even stronger assumptions sometimes built in. So you assume that talk about total functions only. So you don't have partiality. You even have that all terms denote. So even terms like 1 divided by 0 denote. They denote something which you call undefinedness. And you can even prove that this object of undefinedness exists in systems. You may assume things like the law of excluded middle, which we typically do in classical logic, Boolean extensionality, functional extensionality, monotonicity, and so on and so on. So you get the picture here. Often you have built in such a priori assumptions in developments, but then when you want to actually move now with a project, say, in the formalization of maths to another context, say in philosophy and law, and want to apply there this mathematical terminology in the context of arguments in philosophy, for example, as we do in this presentation today, then of course that might be completely unacceptable for that context. So you might need to change some of these a priori assumptions. For example, in philosophy, like today, when we are later interested in proving existence of an godlike being in the demo part, then it might be completely unacceptable to accept that there are a priori existing objects given by the laws of the logic we are employing. What I have been working on for quite some years now is therefore this methodology, which we then later termed logic key, for logical, a pluralistic logical knowledge engineering methodology. And this methodology actually assumes that the object logic itself is an object of study in the setup here. So the object logic itself that builds the foundation for your further development is being formalized itself in the meta logic. And the meta logic, of course, has to be sufficiently expressive. I, for pragmatic reason, take here typical classical higher order logic. But then on the object logic layer, I want to introduce the starting points for further knowledge engineering than explicitly. And thereby make this object logic itself an analyzable object of study in the developments. So you don't a priori make some big assumptions, but you make them not only negotiable, but also analyzable. And this way, then we might get a much stronger support from proof assistance for formalization projects, also in philosophy or law and so on, where the details about the logical assumptions might significantly differ from those you typically would accept in a mathematical context. Well, with Dana together, we have, for example, given an encoding of free logic in classical higher order logic. So free logic, for instance, skips these assumptions about existence I have mentioned and totality. So you can have now partial function and undefinedness, a proper treatment of undefinedness in this logic. And there are papers, actually 4 years ago, I had a talk here in Topos, where we presented work in that direction. Namely, we showed then that using such a free logic encoding as an object logic layer, then you can take then that as a suitable basis for the formalizations of an axiom system for category theory. And we pushed this work then a bit further together with students. So there are papers mentioned here, which you might have a look in, or just check the talk I gave 4 years ago. Well, in the remainder of the talk, you will see this logic pluralistic knowledge representation and reasoning methodology at work. This is actually going back the origins of this methodology. I didn't call it LogicKey at the time, to the years 2007 and 2008. And you see over the years, we have actually dealt with many different logics at the object logic layer. So for example, we have looked into even very expressive logics like hyperintentional higher order modal logic that was in the context of the encoding of Edward Salter's Principia Logico-Metaphysica. So a doctoral student, Daniel Kirschner, looked into an encoding of that in using this methodology. But as I said, so the origins are much earlier. So that was joint work with Larry Paulson actually at the time. And the first article we wrote on that was in the Festschrift of Peter Andrews. On propositional multimodal logics as an explicitly encoded object logic in classical higher order logic. And later, I wrote with Larry that article here that added then the quantifiers so that you can now have quantified multimodal logic, so higher order multimodal logics embedded at the object layer. And the term for this entire methodology that I nowadays often use, namely LogicKey, was then introduced in that joint work with colleagues from Luxembourg in the journal here, Artificial Intelligence. And in that paper, we were mainly then interested in objects logic for normative reasoning and legal reasoning. So dyadic, deontic logics, for example, we studied there as object logics in this work. Okay, but today we will look into this article here that appeared last year in Monatshefte für Mathematik, and that is the joint work with Dana Scott in particular, namely where we looked at the modal ontological argument by Kurt Gödel and, of course, Dana Scott's own variant of it, and studied it then at very details using this machinery in proof assistance systems. So that is, you could say, LogicKey at work in the area of computational metaphysics, now with a particular focus on the modal ontological argument. And that is what I will demonstrate in the second part. Well, this idea of looking at the modal ontological argument also has a history, and it goes back to an invited talk I gave about the early work with Larry Paulson at the Vienna Kurt Gödel Society in 2012. And at the end of that presentation, I was then asked by somebody in the room what I can now possibly do with that machinery I introduced and showed there. And I said, well, you can probably now encode rich expressive logics at the object layer as they are needed for studying arguments in philosophy, and maybe something like a modal ontological argument by Kurt Gödel can now be formalized. I just mentioned that at the time. I had nothing done about it at this point. And afterwards, I was immediately introduced to Bruno Wolzenlogel-Paleo. He was at the time a postdoc in Vienna, and not well at the time. I didn't know that. And nevertheless, he had an intrinsic motivation to work on that modal ontological argument as well. We were introduced and then agreed to collaborate. Well, Bruno wanted to approach the challenge here more from a proof theoretic side. And I wanted to use this particular methodology of embedding object logics in classical higher order logic. And so we agreed to be first friendly competitors. And then half a year later, I had my first success with the technique. I informed Bruno, we stayed in contact all the time. And from that moment on, we then joined forces and continued working together. And also to distribute the work together. And then quickly, the press became aware of that. First in Germany, Spiegel Online, for example. That was in 2013. Tobias Hürter called me, a philosopher that writes for Spiegel, and we had a long interview. And well, I talked him of what we had done and so on. And the article he wrote was actually quite okay. But in that article, he mentions MacBook twice. And that was because I was asked what kind of supercomputers I had used for the experiments at the time. And I said, well, I didn't use supercomputers. It all runs on my MacBook. And I should have said notebook to stay neutral, because see now what happened in the international headlines. So first there was this international article in Spiegel, and see how the headlines changed. So that was original, still okay. A bit, I don't know, putting this Gottesbeweis too much in the headline already, but then the international one already says, okay, computer science has proved God exists, and now it became really international. So in particular, also US media reported, and see the headlines here. I had no influence on that anymore at that point. So is God real? Scientists prove his existence with Gödel's theory and MacBooks. Or here, researchers say they used MacBook to prove Gödel's God theorem. And then Chris Matijek, awarded journalist, God exists, say Apple fanboy scientist. And you see here in the subtitle of that kind of headline, you find how little attention he really paid to checking facts, because he writes two Germans formalize a theorem that confirms the existence of God. Well, Bruno, his name might sound German, but he's neither a German nor an Austrian. Nobody checked it, nobody called us, and so on. So that's a story, a side story on news and fake news. I think in the last years that even got worse. So an important clarification before we start with all that. No, we have not proven the existence of God using a computer. We did something slightly different. We have formally analyzed an argument in philosophy for the existence of God using a computer. And an argument might, as we all know, depend on things, namely assumptions, definitions you start with, the postulates you bring into the game. And it depends, of course, also on the particular logic you're assuming. So what are the rules of the game that let you make conclusions here? And both dependencies are now being explicitly treated in the methodology. So we can talk about axioms and changing them, but we also are interested in changing eventually our logic setting and to see whether the argument still works. That is actually what we have done, and not an ultimate truth for existence of God on the computer. So that should have been clear, but journalists don't care. They just want to create headlines. Well, so I see this work I'm going to demonstrate more on the side of this quote here of Kurt Gödel. He said exact science is possible far beyond mathematics. So he said there are systematic methods for the solution of all problems, including art. Or another statement you find in his Nachlass in the Maximen 5 published, there's a scientific exact philosophy and theology, which are addressing terms and notions at the highest level of abstractness. And that is more what I would say what we had achieved. Namely, we showed that you can have some thing like formal argumentation and universal logical reasoning on the computer. And you can then apply that. We do it here for computational metaphysics, but the same methodology, that's my silent claim here, is applicable to many different other areas as well. You just have to find the right logic that is accepted there, or the right one to be applied there, and make up your mind about the theories you then work in. Okay, another small clarification before we dive then into the second part is that the methodology Logic-Key can actually be used with many different tools. So I mentioned it briefly. I choose at the meta logic layer classical higher order logic for pragmatic reasons, not to make here a substantial claim about that is the best choice at the meta level. Pragmatic reasons because we have already good proof, automated theorem proving support for classical higher order logic. For others, eventually more expressive logic, they are under development, but you might switch at some point. So I often use then classical higher order logic in combination with Isabelle Holl. It's still my favorite tool for logic education. Good proof automation with Sledgehammer, good model and counter model finding support with tools like Nitpick, and it has a powerful user interface, which at the same time might be the bottleneck because you have a steep learning curve. I see that with my students to get familiar with the power of Isabelle Holl system in combination with that user interface. But many provers could be used instead, and we have worked with Koch in one of the papers we published, and my early papers were actually completely done with Leo theorem prover, my own higher order automated theorem prover. So you can apply that with many different tools in principle. Okay, so let's now come to that second part after this opening clarifications. Let's apply Logic-Key to Kurt Gödel's modal ontological argument. And if we have enough time to also look again in Dana Scott's variant of it. So Dana Scott's variant of it, I come to that in a second, has been out there earlier. And it has also been studied and discussed a lot. But Kurt Gödel's modal variant of it, as we found it in the Nachlass, has not so been investigated yet, so there was no formalization so far. All of this is written up in this publication I mentioned earlier, so you might want to have a look at that. And the rest of this presentation is now following very closely what we have presented in there. And I will also then highlight the novel findings that we report. This here is the scriptum that was found in the Nachlass of Kurt Gödel's. So you see it's dated to 1970. And that was also the year when Gödel wanted to talk about it. So he asked Dana to see him, and he shared some notes with Dana in that meeting. Dana took his own notes then in particular also of this year, the modal ontological argument. Well, Gödel asked for confidentiality at the time, but Dana was tempted and presented it in Princeton then in a seminar. And so the word spread about this work of Gödel on the modal ontological argument. Dana, he writes it in the introduction of our paper, regretted that later. Nevertheless, then this piece of work became public at the time. And in my opinion, I would have probably also been tempted exactly the same. It's a fascinating work, and we will have a look at that now. Okay, so you can see here already in the scriptum that this requires higher order modal logic to be formalized. So the definition of a godlike entity you see here says that a godlike entity X is so that it possesses all positive properties. So for all phi that are positive, that is what we read here, X has the property phi. So that is a quantifier over properties. So an higher order, at least second order quantification you see here. And then it's modal, because here is a part where you see that Gödel proves he wants to step from the possibility that there exists a godlike entity to necessity of the existence of a godlike entity. So M is standing here for possibility in German möglich, and this is standing for necessity in German necessarily. So the notwendig in German. So for necessarily, and this is possibility. And you see when you have that the possibility of a godlike entity implies the necessity of a godlike entity, then all is needed in the rest is to show that the existence of God is possible. And you see Gödel here with that proof then, and with the argument on the right hand side, even addresses a long-standing criticism on the original variant of the ontological argument going back to Canterbury, Anselm of Canterbury. And that version of Anselm was criticized that it silently built in the possibility of a godlike being to exist. So Gödel was trying to address such criticism that were brought up over the years, and he
Sorry,
studied the
Christoph.
literature. Yeah.
Are you saying that the modal box on the bottom, that was an assumption, or that was the proved by the step
No,
above?
we prove it. We will see that.
Okay.
So yeah. So wait a bit. You will see. We will prove this implication, and then all you need to show is the possibility of an godlike being to exist. Yeah. Okay. So that is now the overview I've prepared for the rest. And as I said, I can be adaptive. I don't know whether we can go through all of them. And when you have questions, don't be shy. Just ask them. I can try to answer and be just adaptive. Because what I want to do now is first I show you aspects of the methodology. So I first have to show you how I encode higher order modal logic in Hoyle. And then we can look at Gödel's original scriptum that has not been looked at so far, because most of the work so far, and also the discussions concentrated on Dana Scott's notes, the Dana Scott's variant of it. That is slightly different from Gödel's scriptum variant. And here we did first time looked formally at this variant in the paper I mentioned. And we do that with with variations. So first we keep the notion of essence. That is a crucial notion in there. You will see that in a second, that Gödel defines essential properties of an individual, and we keep the definition as it is in the scriptum, and we will show that there's an inconsistency then. So the assumptions Gödel make are leading to an inconsistency. Then we modify the notion of essence, and that is also the same variant that Dana Scott used in his variant, and a varied notion of essence, something that's really plausible to do. And you see then that when you do that, you not only stay consistent, but you get a proof. And we will have a look at that. And then I show you another alternative. So instead of modifying the notion of essence, you can modify the notion of property inclusion, and you also get a proof. Very similar to the previous one. So you have two options here. And this is actually a new, really new contribution. Well, the entire formal study here is also new. Okay. Preliminary. So that is now really about logic here at work in a way. We first have to make the first step. So higher order modal logic in Hoyle. I show you now in the remainder, always the Isabelle development here on the right-hand side of the slide. On the left-hand side, you see comments, and also in the white parts that I will develop step by step, you will see comments. So these here are some unimportant settings we start with. Instructions for the model finder, so parameter settings, or instructions for the parser. So we can forget about that. what we have here is basically Isabelle Hall interface, and in the background we load the theory main that gives you classical higher order logic essentially, and access to the T improving system, the automated T improvers like Sledgehammer and Nitpick. That is an important part for us. So now in that setting of classical higher order logic, I want now to encode higher order modal logic. And I do that by a shallow semantical embedding. And to do so, we introduce types first, a type I for possible words. So we have now an explicit type of possible words, and we also introduce an explicit type for entities, for individuals. Now, the idea of the embedding of higher order modal logic in Hall is that modal logic formulas become predicates over possible words, or true sets over possible words. So you can apply a term that represents a modal logic formula to a possible words, and then the application tells you whether this formula holds, whether this modal logic formula holds in that word or not. So we make Kripke-style semantics explicit in a way. So that means that the modal logic formulas have this type sigma, so predicates over the type I. And modal predicates can then be introduced. So you can now formulate using that type sigma, then of course modal predicates, which you can apply to terms that denote entities. Furthermore, we introduce explicitly an accessibility relation between words, possible words. So that tells you whether from one word you can access another possible word. And we might now introduce postulates on this accessibility relation that are getting us to modal logic S5, what we call modal logic S5. In modal logic S5, you have an equivalence relation as an accessibility relation. So this relation is then reflexive, transitive, and symmetric. And you see we postulate these axioms here. But later you will see the T improvers will tell us exactly which one of those axioms they have used. So they will tell us whether they need all of them or whether you just need symmetry, for example, which will be the case. So now that is the most interesting part. The idea is to have higher order modal logic formulas encoded this way, so as predicates on possible words. So in a way, we have now to provide a definition for our connectives. So the bottom connective, top connective, the negation, conjunction, disjunction, implication, and equivalence, for example. And you can do that. So this is easily done now by showing that they correspond to these lambda terms here on the right-hand side in the meta logic Hall. So they are the predicates that I've been hinting at. So in a way, these simple equations here introduce you now notions of modal connectives using that idea of encoding modal logic formulas as predicates, and they give you then these terms as abbreviations of lambda terms. So that's very interesting. And we continue that now and give definitions or abbreviations in the same style for the box operator using the accessibility relation R. So box phi says, or necessarily phi says, that in all worlds that are reachable from a current world where you are in, so all the V's you can reach from a current world you are in, the formula phi holds. So that's the intended idea of necessity. In all possible worlds, something holds. And then dually, the possibly phi means there exists a reachable world in which phi holds. Okay, you can introduce primitive equality. You can now introduce what we also need later, a notion of complement and intersection of modal properties. You can introduce an exclusive OR based on the definitions we have already, the abbreviations we have already introduced. And most importantly, you can also introduce the quantifiers. Here first, possibilist quantifiers. Constant domain quantifiers. And here the trick is that we know from higher order abstract syntax also that we don't introduce them as new binding mechanisms where you would need all the machinery talking about these binder constructs, but you map them directly to the existing binding mechanisms you have already at the meta level for lambda abstraction. And this way you can continue with simple abbreviations for introducing also possibilist quantifiers for the entire type hierarchy, and also actualist quantifiers when you introduce another explicit symbol, namely talking about existence in a world, so existence of an entity in a particular world. With that existence predicate, you can now introduce an actualist quantifier or a varying domain quantifier that is guarded by that explicit existence predicate. By the way, that is exactly the machinery that free logic also uses. So that connects also that work here to the work I've mentioned earlier on free logic. So the way we handle actualist quantifiers here. So that's very cool. So we have now a modal logic setup where we can work with different notions of quantification. You can introduce Leibniz equality based on the definitions we have already. And finally, what we need, of course, is a notion of validity for this so-called lifted formula. So our modal logic formulas are now predicates. And so we have to say what validity means. Validity is now written with that square, this kind of square parenthesis here. And it does the obvious thing. So it says, well, a formula is valid if it holds in all possible worlds. And that is exactly what this kind of abbreviation here tells you. So the interesting thing here, and mathematicians would only look, of course, at these equations here, that is the essential thing, is that we have identified now higher order modal logic as a kind of substructure of higher order logic already existent there. And we only introduce these kind of lambda terms and we take them as the representative of our modal logic connectives, right? So it's already there. You just have to put on the right classes. And then you want to eventually put some axioms also in, namely constraining the particular modal logic you're in, namely now postulating them as reflexive, symmetric, and transitive. But these are no axioms. These are just abbreviations, right? So it's not an axiomatization of a logic, and that is very useful because we have now a high degree of proof automation that we can inherit from the meta logic layer for that introduced object logic, higher order modal logic here. Okay. The next step is now to test whether this higher order modal logic does its job. So you might now ask whether the typical schematic axioms for modal logic S5 are valid, and you can prove that they are valid. Here BLAST is a theorem prover, and here you see the dependencies. So that axiom corresponds to reflexivity. That schematic axiom here corresponds to symmetry, and so on. You can check whether the Barkan formulas hold or not hold. So you can see here that the Barkan formulas hold for the possibilist quantifier, so constant domain quantifier, but they run into counter models with nitpick when you use the other quantifiers, the actualist quantifiers. You can prove, say, the axiom schemata for an Hilbert calculus as being derivable with theorem proving machinery. You can check whether existential import holds. And for possibilist quantifier, you can prove formulas as criticized before. But for existential, but if you check this existential import for the actualist quantifier, you see that you get counter models. So we have now quantification for both notions. One that comes with existential import, the other one doesn't. You can check the properties of equality. They hold as intended, but they are not, all of them are given, namely the one direction of Boolean extensionality has a counter model. That is exactly what you would expect in a modal logic setting. So that this direction of Boolean extensionality from equivalence to equality doesn't hold. You can check whether you have comprehension, full comprehension. You can check whether modal collapse formula holds or not. Modal collapse formula is a prominent formula discussed here in the context that says if you have an so it says for all phi that are contingently true, they imply that they are necessarily true. That basically says there are no alternative worlds. And this is, of course, a formula that we don't want to have valid a priori in a modal logic setup. It wouldn't make sense to have that. You can check for further things like whether universal property is the same as self-identity and the empty property corresponds to self-difference and so on. So it gets you the flavor, right? And now very important for what we do here is we also need to lift the notions of mathematics we are interested in. Here, that's the notion of a filter or ultra filter. I will later make a connection here to this setting. So here we first introduced notions of set theory, empty set, universal set, subsets for the different quantifiers we have, and the intersection of two sets and complement. And then using those definitions, we can formulate what a filter or ultra filter is. Again, with the varying notions of actualist and positivist quantifiers. So you can say a filter contains the universal set, but it doesn't contain the empty set. It's closed under supersets, and it's closed for intersection. And you have here the two versions. We have here two versions of subset relationship. Right. So now we can look at Gödel's, the formalization of Gödel's manuscript. And I first show you how we run into an inconsistency briefly. So Gödel starts out in his scriptum with the notion of positive properties. And the notion of positive properties, remember, it is then used to define a godlike being as an entity that possesses all godlike properties. And then it boils down to saying what positive properties are. And Gödel gives then axioms for that. So axiom 1 here tells us that the intersection or conjunction of two positive property gives you again a positive property. Yeah, if you have a positive a property phi and a property psi, which are both positive, then the intersection or conjunction of these two properties is again a positive one. The second one here is a very strong axiom. Either a property or its complement is a positive one. And this has also been criticized. So basically, you see here already thinking again in terms of ultra filter, this reminds you to being closed under intersection. And this is something that you can already get in an analogy of totality with other in the context of ultra filters. The definition of a godlike being: an entity is godlike if it possesses all positive properties. We have then a definition of necessary implication of a property. Psi is necessarily implied by psi if necessarily for all y, which have for which phi holds, we also have that psi holds, an obvious thing. And using that, you can define the notion of essence. So a property phi is an essential property of X if all properties of X necessarily follow from that essential phi. So phi implies all other properties of an entity X, and then we call it an essence. So that's a definition that is introduced here. Positive properties are necessarily positive, is another axiom introduced. And now we can prove the first lemma, namely non-positive properties are necessarily so. So it's the first thing you prove, and you see the theorem provers tell you exactly in the end what is needed. So if you call here the sledgehammer tool, it gets you back with that statement, and it tells you, yeah, use axiom 2a and axiom 2b with the inbuilt machinery blast, and you get the pointers exactly to what was used. Very, very interesting for this kind of experiments. Now we get to theorem T1. Being godlike is an essence of any godlike being. Again, provable fully automatically. You get to another definition that Gödel introduces, namely that of existence. X has the property of existence if all essences of X are necessarily exemplified. So we have, here's the definition. So X has the property of existence if all phi that are essential properties of X, we have that these phi are necessarily exemplified. So there exists an X or exists a Y that has that property. So in all other words, we have these essential properties exemplified. And then he says, well, existence is a positive property. And then we can formulate another theorem. If X is a godlike entity contingently, then the property of being godlike is necessarily exemplified. In other words, so if you have a contingent godlike being, then it automatically implies that there are that necessarily in all other worlds the notion of a godlike being is exemplified. And that is then used in this crucial theorem T3 here. From possible existence of a godlike being follows the necessary existence of a godlike being. You can prove that follow automatically, or you can give here an interactive proof as we've seen it on Gödel's scriptum at exactly the same level of granularity. Crucial theorem, because what now is needed is only to continue and to prove that God's existence is possible, because then here we can use this in a modus ponens style-like argumentation to conclude the necessary existence of a godlike being. And for doing that, for proving the possible existence of godlike being, Gödel proposes another axiom, namely this one here, and that reminds you now the other closure property for filters, namely being closed under supersets, and here it's being closed under necessary implication as we have introduced. So if P is positive and phi, if phi is positive and if psi necessarily follows from psi, then also that psi must be positive. So properties that are necessarily implied by a positive property are also positive. So that is this additional closure condition we get in. But now a check with the model finder for consistency, which you can regularly do in these developments, tells us, well, I don't find a model, so it doesn't succeed anymore. Before it always succeeded. That, of course, triggers a check for falsity. And in fact, we can prove falsity with the automated theorem provers again. And the reason we can prove falsity is simply because of the empty essence lemma, which we can also prove. And that says that the absurd property, the empty property, or the property of being self-difference are essential properties of any entity X. And this is, of course, quite unintuitive and problematic. And this is also the reason why we get this inconsistency here. So we need to eventually fix the notion of essence. And this is what we did here in the second step. So we fix the notion of essence. Everything up to here is as before. Here is the notion of essence. Now we add the conjunct, and that is also what Dana did in his notes. Now we add to that, and the definition reads now as follows. A property phi is an essence of an entity X if X has that property phi, and that is the other condition we had before. So now we explicitly require that X, it must be able for X to have this property phi. That kind of excludes the empty property, because the empty property can't hold for any phi. That is by definition of the empty property, or by its very nature. So now we can continue, reuse our machinery, all the proofs, we can see whether they fail. Now nitpick tells us here we get a model after introducing this axiom 4. So we can inspect that model, you can look at it. Often these models you get then from nitpick are very intuitive. You can look at them and check them. And then you try to proceed, but I wasn't successful. I was getting stuck here, unfortunately. So the last step was now to prove theorem T4 with a lemma in between. But I did get stuck. I couldn't prove neither of them. And why is that? Well, if you look at Gödel's scriptum, you find for axiom 1 an interesting footnote, namely the axiom 1 tells you if a property is positive and another property is positive, then the conjunction of these two properties is positive. The intersection of this property is positive. But Gödel says, but you need that for any number of summons. So not only for building finite conjuncts here, but eventually also to build an infinite conjunction of properties. So in third order logic, we don't have enough time to go now into the details of the definitions, but in third order logic, you can formulate that generalization here. So you can formulate now that generalization of axiom 1 that lets you build these infinite conjunctions, infinite intersections of positive properties. And if you do that, then you can prove now the lemma, godlikeness is a positive property, and you can prove a godlike entity possibly exists. But you need to modify the definition or to generalize the axiom A1 for doing so. So we are done. So now easily necessarily existence of a godlike being follows.
And Christoph, you asked me to interrupt you. Yep. Okay.
Yeah, we have 5 minutes. Yeah, I continue and I stop then at 1950 sharp. And I leave the rest of the demonstration eventually for interested discussion. But here's an interesting point now. An interesting point is you can now inspect the proof and you find that only symmetry of the accessibility relation was used. So that is a proven modal logic KB, right? You can now check further things. Modal collapse indeed follows now. So the modal collapse formula that tells you basically now we don't have possible worlds anymore. There's just one world as it is. And that follows from this theistic theory of Gödel and might be controversial and highly criticizable and has been criticized. We can prove that. Also in modal logic KB. And you can now give here and investigate examples of positive or non-positive properties. Self-identity is positive, self-difference is not. You can check what essences, properties about essences. So entities are uniquely characterized by essences. You can ask for monotheism. Well, that might depend on what notion of equality you use. And you can check whether the notion of positiveness is an ultrafilter, as I already hinted at, and indeed it is. So you can prove that the notion of positive properties is an ultrafilter. So as with the look of a mathematician, with that machinery of a modalized ultrafilter, you can now prove that. But we need this machinery, the modalized ultrafilter, the notion of mathematics for an ultrafilter, now on the level of the modal logic to connect the things here. And you can check for consistency. So nitpick gives you still trivial models. Again, you see only modal logic KB was needed here. How about logic S4? I don't know yet. That is an open question. I couldn't finish that one. Logic S4 doesn't work with the symmetry of the accessibility relation, but it works with reflexivity and transitivity. That is something to further look into. I now have another interesting discussion here that I definitely want to bring in the talk. And this is, remember again that we had to step from axiom 1 to the generalization of axiom 1. This is an interesting thing. So with axiom 1, the proof didn't succeed. With the generalization, the proof succeeded. So if you do now the following, if you assume now with Gödel, we know that he had this nuanced realist position that the objects of mathematics, including, for example, natural numbers, have some real existence or do really exist, not as physical objects, but as non-physical objects that have a real existence. Then we start out with at least countably many positive properties. This is because of the totality axiom. You know, either a property or its negation is positive, or its a complement is positive. Now, if you have something like the natural numbers, then you have the unit set. So the property of being equal to 1, the property of being equal to 2, and you have the complements of that, the property of being not equal to 1 and the property of being not equal to 2. And either one of that has to be a positive property. Well, it turns out that the property of being not equal to none is a positive property. It tells you that God must be different from the natural number 1. God must also be different from the natural number 2 and so on. But you have now already infinitely many positive properties. And with the generalized notion of the axiom A1, you can get now, of course, like in Cantor's construction, power set construction, you can show that you have now uncountably many positive properties implied when you start with such an assumption. And we did that formally as well in a paper to come out soon in the festschrift of Larry Paulson. So we can look at that. So to keep it short, you can go now and you can also adapt property inclusion, a different notion of property inclusion, and keep the notion of essence. And you also get a proof in logic KB. I don't do that here. I also skipped the thing about evil. Short story again. You can either prove that evil does not exist, or you can show with an adapted notion of evil that when you do that, that the notion of evil is essentially the same as the notion of God. So when you switch all the axioms, then you get back. So evil is problematic here in the context, and you might want to question me about that. And well, what I also don't go into is then talk about the variant that Dana produced. There has been lots of work reported on that already in the literature, and also our early papers did that. So I skip this as part as well and just come to the conclusion. Namely, what we have seen is the logic key methodology at work in computational metaphysics. And it was crucial here that we can vary the object logic in addition to vary the particular assumptions we make using that object logic. So the axioms we postulate and so on. And what we contributed is a first formalization of the original variant in Gödel's manuscript. And the modified version with property inclusion is exactly also a new variant. At least I don't know whether this has been discussed already. There are various minor other insights gained in the study, and I hinted at some of those, also with countability and uncountability of positive properties, and see this forthcoming paper in Paulson's Festschrift where I dive further into that. Future work, various open questions, in particular to look at logic S4 again, a further study of which we did partly in here of this generalized notion of axiom A1, look into comprehension and impredicativity and so on in the context. So you could give up also assumptions on comprehension, for example. But in general, future work is, in the sense of Gödel, to show that there are systematic methods that can also be applied in other disciplines using such a methodology, for example. And here we just hinted at the possibilities that we have. I think way more can be done by rigorously using this kind of approach, where you make the object logic an explicit object of study first before you develop your theories on top of that. Thank you.
Thank you, Christoph. Okay, so we have some time for questions. If you have a question, press the React button on the bottom and raise your hand.
Dana's waving.
Okay, or just unmute. Sounds like someone did.
I was pointing out Dana. It looks like he's trying to talk. Dana, you're
Oh,
muted.
okay.
So, Christoph, thank you for showing how to experiment with logics. People have been experimenting for a long time, but you've given a very wide way of systematizing experiments. I have two quick questions here. Some years back, you spent a lot of time with Ed Zalta on his metaphysics. Is there something more to do with Zalta's theory? That's my first question. And my second question is, we know many colleagues working today axiomatizing various forms of category theory and Agda, and I wonder how that kind of work might meet up with the kind of formalizations you're doing. So that's two questions about Zalta's metaphysics and about using Agda.
Yeah. Thank you very much. Also great to see you here. I'm really pleased to see you. So the work on Zalta, that was an impressive line of work. I mentioned it, that were needed to actually encode Zalta's Principia Logico-Metaphysica. We needed to dive into a quite different starting point at the object logic layer, namely this hyper-intentional higher order modal logic he starts with. And the hyper-intentionality is one aspect to address here, but another one is actually that there was a quite a big discrepancy between the classical logic, higher order classical logic we use here, and which is based on functions, and the logic, as the basic logic assumptions that Salter does, it's a relational logic where you even had originally, and still there are, restrictions on the logic syntax, even in terms of being a relational logic. I don't want to go into the details, but the key point here is there was a big discrepancy that was way different from the meta logic we used, and it was quite a challenge to actually get the starting point right. So to encode exactly this kind of starting point as an object logic. And a PhD student of mine, Daniel Kirschner, it was successful here, and then put on top of that actually a partial development of Salter's theory. Well, we have produced 20,000 lines that actually go quite a way in formalizing Salter's work, but there would be more to do to really finish that, and they are both still in contact, and they are both still interacting, and there's eventually more room for even another such a PhD-like project to continue that. But they are still in contact, and this is ongoing area of development. So I don't know whether if Ed here is in the room, he might even himself report a bit on that, further plans there. But yeah, room so much of further developments. And of course, it would be also interesting to see now in another project what happens if we change the foundation, classical higher order logic, for instance, to another one, let's say a foundation based on dependent types, like in Lean and so on. Can we transfer the work we have done, the 20,000 lines of code, if the meta logic is changed? What about the degree of automation and so on? Can eventually tools like large language model help us to transfer that word from to the connection from the setup we have developed to, for instance, a setup as in Lean and so on, or in other proof assistance systems. So Lean I just mentioned as an example, because at the moment there's such a dynamics behind the development of the Lean team improver. So many interesting questions you can raise here. Also about the simplification of eventually Salter's theory from the input we give and from the interaction we give. And there were such simplifications already being contributed, because initially Daniel Kirschner found an inconsistency or paradox that Ed was aware of. And he thought he took enough precaution to rule it out, but it was nevertheless there, but very hard to detect. And Daniel then found this paradox or rediscovered this paradox in interaction with Isabel, and he helped to fix it with the machinery. So we might be able to further contribute in improving the basic theories, and that has happened over the years and is still ongoing. The second one.
Okay,
category.
just to quickly let you know, we have
Yeah.
about 3 minutes and 2 more questions.
Okay.
But
So
yeah.
category theory. Yeah, we did the experiments with free logic, and it would be also now a nice with free logic embedded on top of classical higher order logic. And well, if there were resources and more PhD students available, we could have another one looking in the same fashion Daniel did that into, let's say, connecting the works that's currently being done in proof assistance like ACTA, which have a different logical foundation, of course, and whether we can convert that, for instance, here in our setting. Interesting question, and that we stopped at some point, but that was more or less because I was running out of student and moved to another university. So there's room for another PhD project that would look into category theory again and try to rebuild the current libraries that are built up in other contexts using this machinery here.
Okay, thank you. And I think we'll have time for one more question, and then we'll go to then we'll break, and anyone who wants to stick around can ask more questions. But we have Alex Ross.
Yeah, entschuldigen, Herr Professor. I'm sorry, I just came a little bit late. Don't think I'm kind of like a Doomkopf, but literally don't understand what this lecture about. For me, it's like a a lot of manuscripts right now. Can you explain to me in a short term? I'm sorry about this. I'm sorry to ask such a stupid question just in a short term. What this lecture about?
Well, two things was that picture here, so that instead of directly starting with some logical foundation you fix, you might be interested to explicitly define your object logics. And I showed a technology that does that. And then use that object logic, which was in the example I gave today, a higher order modal logic, different variants of higher order modal logic. And then you use that to analyze arguments, for example, in philosophy, where just proper classical logic, for instance, would not be accepted for that particular argument. So that is what I demonstrated. And then we looked as the object of demonstration into the modal ontological argument. So that was just an example argument which you can analyze now with varying not only axioms, but only varying, for instance, the notion of quantifiers you're interested in. And we had all different kinds of variations we played through. So that is in a nutshell. So it's about logical pluralism versus logical monism, where you just say, that is my logic and use it or don't. Well, that is basically a key message to take away.
But we should emphasize that you mechanize doing it so that you're able to be really exact about it, and you found
Exactly.
things that go wrong. Yes, through the mechanization. I think that's the extra important thing.
Yeah, so that step is being mechanized. It's not just the pen and paper work in the background and then you start from there, but that part is being explicitly part of the entire mechanization. Yeah.
Very nice. Okay, thank you, everyone. Let's thank Christoph again.